So welcome to chapter 10. It's called Numerical Methods, and here you can see the main skills that we need to learn in the chapter. So first of all, we have locating roots. So locating roots, the idea is going to be that we are subbing in these values. Let's pretend one of them, say, is a positive, one is a negative, and we will say that because one of them is positive and then the next one is negative, it means that somewhere in the middle there is a, and this is a key phrase, there is a change in sign. Okay, that suggests that there is a root. A root, remember, just means when it's equal to 0. Yeah. One other thing, we will need to be using the word, as we do this, continuous. Continuous just means that, as you can see in the picture there, there are no gaps, there's no asymptotes or anything like that. Okay, so that's going to be the first part of the chapter. Next, we're going to talk about using iteration. So you might notice that this is very, very similar to GCSE. We're going to have some sort of, well, if we put a 0 here, we're going to have something here where we rearrange. One of the x's will go on its own. We'll have some other sort of function. So we show that. And then if you compare from here to here, you'll just see that this notation has crept in. So the idea is that we will start to use iteration. Iteration, that's the one where somebody gives you a value to start with. You press equals. You press equals again. You know, you change after the first one. You change this one here to ANS for your answer. So the idea is that you use an answer sort of as the input of the next part, and this process can solve some equations. So there's nothing too radically different, in fact, in the number 1 and number 2. Number 3 is where things will be a little bit new. So the idea here is going to be, let's get that one out of the way. The idea is going to be that we have a new formula to apply something called the Newton-Raphson method. This is in the booklet. Okay. It's similar to iteration. It's a process that you can use that will give you better and better answers to find the root. So this whole chapter then is all about roots. It's about identifying, yes, there is a root, using iteration or the Newton-Raphson process to then find the root. So let's have a quick look at this one here first. So why do we need numerical methods? Well, the idea is that sometimes when we want to solve an equation and we want to solve it to 0, it can be very, very difficult. I'm not going to show you the second one, but it is actually horrible. But how about this one here? So if I said x minus cos x equals 0, you would find it very, very difficult indeed to solve this one here. So we need to have some sort of process that helps us solve things like this. Okay, because you would say something like x equals cos x maybe, but then where do you go from there? Yeah. What's not obvious is that looking at this graph here graphically, there are methods where we could confirm that we had a root here, and we could actually get a pretty good answer to this one. So first sort of mini question, show that f of x equals e to the x plus 2x minus 3 has a root between these. So what are we going to do here? Well, as we previously said, okay, we're going to sub these in. So we're going to find f of 0.5, and we're going to write that to quite a few decimal places. And then we're going to write f of 0.6 and write that to quite a lot of decimal places as well. What we should find is that there is a change in sign. So this is a key phrase for us to write. Okay, and they will give you, as you can see here, they will give you a continuous function. So you need to mention that as well. So finding them, change in sign, continuous, and then a minimal conclusion. So there is a root at blah, 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 something like that. So let me just show you that all in effect. So if we get rid, not that one there, if we get rid of that one there, you should see the following. Okay, so you need all those elements there. It's a 2-mark question, so very, very nice. Now, what we have basically done here is, if I just show you this, we've worked this out and we've worked this out. So you see here, if it's not drawn, I am assuming, aren't I, that it's continuous. So as you might be able to guess, there's a number of problems with this because it's not necessarily always like this. For example, there could be an asymptote in between. That would cause a problem. If I had that there, then potentially there might be no root. Okay? So let's have a look at the next part. So on the board here, just two examples of why looking for a change in sign can fail. Okay? So why can the change in sign fail? Well, here, this is because there could be an asymptote. Okay? What's the problem here? This is something that I've seen come up in papers a few times. If the two that you try are too far away, they'll both be negative, won't they? So it doesn't mean that there's no sort of root. It means that there might be two roots. So sometimes the sign change method can fail if there are an even. Okay, this is the one that I've seen in papers before. An even number of roots. Okay, let's take a look at this one then. So a slight variation of the question is as follows. G of x equals all of this stuff here. The root of g of x equals 0 is alpha. Where's this talk of alpha come from? Well, we can say that, you know, alpha is one root, so you might be thinking, why doesn't it say x? Well, it does. X equals alpha just means one of the specific roots. So sometimes it's useful to give them different names, the different roots. So alpha, beta, and so on. Okay, so it says, choosing a suitable interval, show that this is correct through decimal places. So what we're supposed to do is we're supposed to use sort of our GCSE knowledge of bounds. Upper bound is easiest to do first. Correct to three decimal places. So that's the upper bound, isn't it? And the lower bound, I always just think it's slightly easier doing the upper bound first. Okay. These are the values then that the question is effectively asking us to check. Okay. So let's move those out of the way. And let's see what it says. So when we do the first one, we get a very, very small negative value. That means we're very, very close to the root. And then when we do the other value, the bigger value, we get a very, very, very small positive value. So there's a change in sign in the interval and the function is continuous. Therefore, okay, so those would be the key parts there that we would need to write. On to the next part. So a question like this is also another one that we can do. So let's move those pieces here. So using the same axes, sketch the natural log of x and 1 over x. Explain how your diagrams show that natural log of x minus 1 over x has only one root. Okay, so there's a few things going on here that are not obvious. So first of all, we can think about this. So if we think about roots, we're really talking about where the natural log of x minus 1 over x equals 0, yeah? Which is the same as the natural log of x equals 1 over x. So by thinking about them as separate graphs and how they interact, that's the same as thinking about this situation, okay? So the intersection, yeah, the intersection of these points here is the same as the root of this. Okay, so once you find that value by, you know, looking at this one and this one, you've actually answered this question here. So let's show you what that looks like. So if I delete that one there, this is what our graphs look like. Now, natural log of x, you can kind of work out what this one looks like by thinking of y equals x and mirroring an e to the x graph. That's one way that I find helpful. And you can see that clearly there just seems to be some sort of point here where x is some positive number where this is happening. Then part B says, show that this lies between this interval. Okay, well, you know what we're going to do. We're going to sub them in. We're going to say there's a change in sign because it's continuous over this interval. So let's get rid of that. Okay, so this answer here would not get full marks because you must say that it is continuous as well. And then if we move that one out of the way there. If we move that one out of the way, can you see we've got the other version of the question that we've just done, which is 1.7635, 1.7625. You would do those and you would in fact find a more precise way to verify where the root is. So this is all about the same root, this question. We're just getting more accurate, aren't we? Over here, we're talking about 1.7, 1.8. Over here, we've really, really narrowed it down. And then that also just seems to match what's going on in our diagram. Okay, so that should help you with the first part of the chapter 10A.